a Ernesto Lupercio. Hay muchos jóvenes acá y Ernesto tal vez debería contar un poco, yo cuento lo poco que sé. Ernesto estudió matemáticas en el Instituto Politécnico Nacional y él contará cómo. En algún momento, por alguna razón, conoció a Samuel. Y gracias a Samuel, Ernesto está aquí hablando con nosotros porque fueron sus cartas de recomendación lo que les abrió las puertas a muchos matemáticos que están aquí y que ustedes ya son la segunda o tercera generación. Entonces, gracias a Samuel tenemos a Ernesto, por lo tanto es un placer inaugurar este centro por tercera vez con la charla de Ernesto Lupercio.
Ahora cuéntate.
It is quite an honor to be speaking here.
Sorry.
It is quite an honor to be speaking here in Sam's conference. As Bernardo pointed out, my career would be unthinkable, could probably not exist without both the inspiration that Samuel emanated to all of us in my generation and several previous generations in mathematics. It is not at all a coincidence that so many of us became topologists rather than analysts or algebraists. It was the profound inspiration of Sam, on the one hand. But not only that, as Bernardo said, he also walked the walk, the actual support in so many ways. Not only the recommendation letters and the time to talk to you and the kindness and do you need a plane ticket to go there? I mean, everything. His generosity felt so authentic, so not faked at all, and it was immense. And it was. It's hard to talk to him about him without him being here. I was just saying to a couple of friends just a couple of days ago. Did he really pass away so many years ago? I mean, it feels like I should just walk to the coffee shop and run into him and talk mathematics. So I was extremely honored to have met Sam, who was bigger than this. In any case, I decided today, I've been working on many subjects recently, but I decided to talk about this particular one because it dovetails, it connects with Fred's talk and with the mathematics of Santiago. So I have decided to talk about this, that is very related to Sam's work. I have to say though, before I start, that even my PhD thesis, I was using Brown-Gitler spectra, so his influence is all over my life. In that homotopy theoretic era of mine, and in this more geometric era, Sam's influence is always there. I dream of him very often. Okay, so I'm going to talk about two fields of geometry that we have discovered in the last few years. The first one is Toric geometry of the quantum flavor. Toric geometry, of course, is a reasonably recent field of geometry in that it is from the late 20th century, the explosion of Toric geometry, and on to the 21st century. And it was always intriguing to me, Toric geometry, in its peculiar combination of subjects, how different subjects would interact in Toric algebraic geometry. Toric varieties, of course, have this torus that is a complex torus, and somehow X compactifies the complex torus in a particular fashion. And there is not a unique way to compactify a torus. There is more than one. For example, if you take T2, there is two obvious immediate compactifications. One is, say, P2, why not? And the other is, why not, P1 cross P1. And they are different, and they both compactify the two-dimensional complex torus. All the various possible compactifications of the two-dimensional complex torus would be all the possible two-dimensional toric complex toric varieties. The compactification that I am allowing are a little bit stronger than what I just said, in that the action of the torus extends to the whole of P2 or extends to the whole of P1 cross P1e in a holomorphic fashion. So the natural action of the torus on itself extends to the compactification in an equivariant fashion. And so all these possible equivariant compactifications are all the possible toric varieties. And so there is the subject of the so-called toric varieties. In the last few years, little by little, from very many different sources, like quantum entangled states and very many different sources of ideas, of thoughts, Ludmil Katsarkov, Laurent Merseman, and Alberto Berkowski, sorry for the I, not the Y, thanks Javier, and myself primarily have been developing all these fields of quantum toric geometry. And what is the main point of quantum toric geometry? Well, while the main point of toric geometry is that there is these combinatorial objects that tell you how to compactify the torus. In this case, it is a triangle, while in this case it is a square. This combinatorial object that appeared in polytopes, that appeared dually in Fred's talk. And then you have this theory of toric geometry. Quantum toric geometry starts by thinking, what would happen if rather than taking classical tori, I took quantum tori? So I'm going to take quantum tori, I'm going to compactify them. But what are quantum tori? Well, there are things that are written with a calligraphic T rather than a blackboard bold T. And what I mean by this is that they are not scalar varieties in the classical sense, but they are non-commutative scalar varieties. They are non-commutative spaces. Now, there is all sorts of products in the market, or software in the market, or whatever, to deal with non-commutative spaces. We have here several experts on the various products in the market. Omar Antolin is an expert in the infinity category approach, and there's many ways to do it. But in any way you may want to do it. Javier himself is an expert in one of the ways to do this, that is foliation theory, the theory of holomorphic foliations. But in any way you may want to do it, take a quantum torus. And then how can I equivalently? Well, of course, once you have the category of non-commutative spaces, you can have group objects in the category of non-commutative spaces. Why not? And then you can ask, what does it mean to equivalently compactify this non-commutative space? And then you can answer this question and produce the theory of non-commutative toric. But because torus are very commutative, we called them in the past non-commutative Toric varieties, but the name was very confusing because everything is so commutative, and then we call them non-commutative Toric varieties, and even the name non-commutative torus can be exceedingly confusing. But there's another name called the quantum torus for the same object, and so and because another input in this beautiful theory of Toric varieties is that Toric varieties are integrable mechanical systems. Well, quantum Toric varieties, as expected, are quantum integrable systems. So why not call them quantum Toric varieties? So I guess that we have decided that the name is quantum Toric variety for these animals that fell on our laps. Okay, so there it goes. So quantum tori, well, to be very geometric, we can think of quantum tori in terms of foliations. Well, a quantum tori, everybody will tell you that a quantum torus is something in which the spatial coordinates, and today I'm going to take this real parameter. Theta is going to be a real parameter, so real, theta is real. Okay, so in which the coordinates don't quite commute, but yx, I apologize. Thank you so much, Razan. So the coordinates don't quite commute, but they have this slight non-commutativity. This appears for the first time in the legendary paper of Heisenberg, Jordan, and Max Born that gave the Nobel Prize in physics to Born and Jordan, and Heisenberg, but not to Jordan. Born and Heisenberg. So this subject appears for the first time in the classical paper of in quantum mechanics, and well, this is what it is. But it is an extremely beautiful observation by Alan Kohn, who will be a ghost haunting this talk, that this can be thought of as the modular space of leaves of the Kronecker foliation on the torus. So if you take the torus and you take this foliation that appears, so you take the plane, you take the universal cover of the torus, and now you take all parallel lines with certain slope, all of them. I'm going to parameterize the slope by theta somehow. And now you take the quotient, this foliates the torus. And you can ask, is there an algebra so that a spec of the algebra, well, maybe this algebra, so that a spec of the algebra is the moduli of leaves? Is there this algebra, so the spec of the algebra is the moduli of the leaves? And the algebra is this algebra. But the spec is not. The spec is a non-commutative space, stacky spec. So it's not just ideals and blah, blah, blah. It's a little bit more than that. Nevertheless, the moduli space of leaves of this foliation is entirely described by this non-commutative algebra and vice versa. This non-commutative algebra entirely describes this foliation. This is a beautiful observation by Alan Kohn. If you want to see it in a bit more stacky fashion, then you say that you take the two torus, the two real torus, and you divide by the action of the real numbers on it, of this flow. You divide it. Of course, you get a non-house of space when you take the quotient. But if you're willing to deal with non-house of manifolds or whatever, this is a stack. This is a stack. Very non-separated stack, but it's stack. And of course, by taking a transversal to the foliation, you get the same stack. Just by equivalence of categories, this category of the little circle here is the same, the groupoid of the little circle here is the same groupoid as that of all of the torus with the flow, with this canonical flow. So that's okay. So that's the non-commutative torus, or quantum torus. And there is an important dichotomy. Either the slope was rational, or it was irrational. If the slope was rational, every leaf of the foliation was a torus knot. There we have a 3-2, slope 3 halves or whatever in the picture. So it was a torus knot. And the quotient was Hausdorff, and it wasn't all that bad after all. If I divide by this torus knot, I get a circle. Well, I have to remember, because I took the action of the reals and not of the circle, I have to remember that there was a set stabilizer at every point. So there's really a gerb there in the quotient, in this circle. There's this little gerb there, but you can ignore that fact if you don't like it right now. But this is a rational case, and it's very simple then. If you just remember that the gerb is a z gerb, then there is another circle, and then you recover the torus. You did nothing, because you are dividing by a contractible space, the real numbers. So homotopically, you should get the same. There is no doubt about it. Okay. But if theta is irrational, well, then you are in quantum world. Rational, not so quantum, irrational, quantum world. Rasban will complain that yes, it's quantum already for rational. I kind of agree, it's not equivalent though. But anyway, we have that, and now I'm going to use the very important fact. Okay, I'm going to take the transversal as I said. I'm going to take the transversal as I said. I'm never going to really take the torus. I'm going to take the circle or C star with the rotation. I'm going to take C star with the rotation rather than the torus. And on the one hand, but I'm going to even do more. I'm going to take the logarithm. I'm going to take C with a linear action, an affine action. So I want to do everything in additive notation. I want to do only additions, never multiplications. And I want to do that because, after all, toric varieties are varieties over the field in one element. So quantum toric varieties are going to be non-commutative spaces over the field in one element. So I want to take the logarithm. Anyways, I take the logarithm. And of course, I'm going to do this in higher dimensions. And of course, I'm going to take other, so I'm going to take z to the n, one of those, and I'm going to send it with a group homomorphism, abelian group homomorphism, into R to the whatever, D. I don't know. And n is going to be possibly large. So that, think about it, you have this z to the n lattice, and you're sending it to R to the D, and of course, if n is bigger than D, and things are random, you're going to probably get a dense set inside R to the D. Just imagine the three-dimensional lattice projected at random into R2, and then you get points all over the Phrygian place, I mean, all over the place. So I'm going to call that a quasi-lattice. So in toric geometry, there's this important ingredient called a lattice, or an integral lattice, or something like that. Well, in quantum toric geometry, there will be this important ingredient called a quasi-lattice inside Euclidean space. Okay, in any case, well, I do the same. And for this gamma thing here, this gamma, well, I'm going to take gamma inside RD. For this thing, for this gamma, I'm going to define the quantum torus associated to that quasi-lattice, associated to that gamma. I'm going to define the quantum torus associated to that gamma. So, there. So that's the quantum torus, and this homomorphism, I rather call it the Planck's constant. The several Planck's constants, the several Planck's lengths, I should call them. But anyway, I'm going to call it H bar. So just as to reminder that it is my deformation parameter. So there will be a modular space of these objects, of this tori. There will be a modular space of this tori, and this will be the deformation parameter. H bar will be the deformation parameter of the modular space of this quantum tori. So that I can move in the universe of this quantum tori freely. And of course, a modular space of stacks. All the Kodaira-Spencer theory necessary to make sense of what I just said has been very carefully developed in a beautiful, remarkable work by Laurent Mersman. So the Kodaira-Spencer theory for stacks and of enormously general kind. And so what I'm saying is right. Okay. In any case, if I take the standard basis, I can look at the images in a Euclidean space. I have these Planck lengths or whatever, some data. Anyway, I don't know, maybe I have to make it a tad bit smaller, that. Well, you do what you can. This is the situation, quantum Toric varieties. So quantum Toric varieties, X, calligraphic X, because they are non-commutative thingies, are equivariant compactification of quantum tori. So an important datum is the quasi-lattice in which we are living, just as the lattice in Toric geometry was important. And to compactify one of these, I need, in the classical view, what do I need to compactify a torus? I need a fan. To compactify a quantum torus, I need a quantum fan. So the quantum, what is a quantum fan? This is a quantum fan. A quantum fan is a fan, of the old-fashioned fan, but a little bit different. Now the rays are allowed to land on any point in the quasi-lattice. So they have much more flexibility, not only on an integral lattice, but on any point in this dense red set of flies flying around. So on any point of the quasi-lattice, I have a ray. And have one of these rays at any point of the, they could land. I have to remember these lengths. In the past, the theory said, look at the first integral point that you hit. But now, this doesn't make sense, so you have to tell me. I'll tell you why it makes sense in the chimeric world, but just in a second. I'm talking about the classical quantum mechanics. These are entangled quantum states. So, we have this, and this is a quantum fan. A quantum fan is almost a fan, but we have this H bar thing. And remember, the intention of writing H bar is that I can deform. So I can deform. There's a modular space of quantum fans, while there is no modular space of fans. So there is a modular space of quantum fans. So these are, in Fred's talk, these triangulations of the sphere of polytopes or whatever. But now I really care about the geometry, because I don't want only the moment angle complex, but the quotients. I want the toric thing. So I care about the geometry, and I want to move the geometry around. So I'm allowing them to have moduli. So, a quantum fan is irrational if gamma is not discrete. You see it all over the place, if it is not discrete. The classical fans, well, is the rational thing. Essentially, rational fans are the classical fans, the classical toric geometry. And now I have more. I have the irrational ones. There is another theory called stacky toric manifold varieties, whatever, and it's also a subtheory of our theory. I will not mention it because it's less well known, but enough is to say that it's also a particular case of what I'm doing. Okay, so there is morphisms of these things. I won't spell them out because it starts getting technical, letters flying around, but it is what you think it is. It is what you think it is, and exactly nothing else. You have to be very, very extra careful, but we have very good definitions now, and they work very well. So there's morphisms of funds. So we have a category of funds, of quantum funds. And, no, it doesn't matter. Yep, I have lost my... Okay, let's see if I can... Well, whatever, it's not so important. There is formulas, but I'll explain what this says. It says that if I have one of these quantum funds, to every one of the big things in the fund, anyway, I don't have really time to spell this out, I can tell you. To any one of these ones, I can associate a chart, a stacky chart, for a stack. So I can give you a stack atlas for the quantum toric. So this is an algorithm, this is a formula that tells you, if you give me a quantum fund, I'll give you a quantum toric variety, that is a stack. And to every one of these things, I'll give you a stack. It's more or less like an orbifold chart, but a little bit more extreme, because the action is, you see, it's not non-Hausdorff in the quotient. So it is the topological space of the quantum toric variety would be non-Hausdorff. But it's just what it is. It's just formulas with lots of letters that tell you if you give me one of these cones, I'll tell you a chart for the stack. And the charts glue well. So it's a good stack. And it's not only stack on the usual category of complex manifolds, but it's also stack on a more particular category of quantum funds. Anyway, let's see. There is more on that here. So this is the so-called change of charts. If I want to change from this chart to this chart, I have to give you formulas, and I have to check that this is a good stack, but I'm not going to do all that. I'm just going to, and here is the gluing, how you glue these charts to produce this stack. But, of course, the upshot of all these formulas and all the resulting calculations is that you have here quantum funds, and you have here quantum toric varieties, and then there is an equivalence of categories between quantum funds and quantum toric varieties. And you need all these formulas to do that. In these formulas, it will be, but let me just point out, though, that coming back to this theme of the fact that we're working on the field on one element, I will have all the time to take logarithms. All the time I will have to take logarithms to do the gluing. And then the gluing will be additive expressions on these lattices. This is the interesting formula. This is the interesting formula here. And this tells you how to glue the different stacks associated. I can associate a stack for this, stack for this, stack for this, stack for this. But then I have to glue them. And this formula tells you exactly how to glue these stacks. These stacks, look at the gluing formula, though. This is almost essentially the quantum torus. But when taking the logarithm, I can close it up. I can close C star into C, but only on one side. And that's what I do. For every quantum, this gives me a quantum torus, and this. So idea, I take this, I straighten it up, see the quasi-lattice, give me a quantum torus. Look at this, straighten it up, see the quasi-lattice, give me a quantum torus. Look at that, straighten it up, give me a quantum torus. I close the quantum torus from one side. I close from one side the quantum torus, but now I have to glue them to get something compact, a compact stack. Well, thanks to the fact that I can take logarithms, I can do the Euclidean using only additive structures. And then I get the whole stack. Thanks to the existence of the logarithm. So this is important. Anyway, an example. This is nice fun. And if I take this quasi-lattice, this is the usual quantum torus that I started with. It's just the usual quantum torus. And when I compactify using this thing that I did, what we get is a quantum P1 associated to that theta, to that irrational theta. I get this quantum P1 that has, here it has a quantum torus, and then I have 2 points that compactify it in a very particular fashion. And it gives me a Kähler stack, no doubt about it. It is a Kähler stack. So I get this Kähler stack that is the equivariant compactification of a quantum torus, and the formula is here. Okay. And you can do more. Even in one-dimensional, notice that because of arithmetics, I can get more and more complicated, more and more, Bernardo would tell me, B fields. I could get more and more B fields, more and more complicated lattices inside, and I can still get a quantum P1 with all that level of arithmetics inside, in the associated quantum torus. So there's a lot of arithmetics in this structure. Okay, so we have quantum geometric invariant theory. So as expected, as Santiago would immediately tell me, quantum geometric invariant theory is also called the Gale transform. So remember, I have these Planck vectors. I don't know, you remember. I have the Planck vectors. I have these Planck vectors there. And then I apply the Gale transform. Now we have a completely Grothendiekian way of talking about the Gale transform, but not for a talk today. But Laurent slowly have realized a completely categorical way of saying this without ever mentioning nothing. but I think it's good for a talk to just write a formula. And so you write the Gale transform. And, well, the Gale transform allows you to go from these parameters, Bi, to some parameter called lambda. That is a complex parameter. This is a miracle. Somehow the Gale transform takes these real parameters and assembles them dually through a baby mirror symmetry kind of transform into complex parameters. This is a Phrygian miracle occurs. No? Then these are complex parameters, and then this, remember, was my deformation parameter, and it looked real. And all of a sudden, Gale transform intimates to you that it was a complex deformation parameter in the modular space. So it is a complex parameter, and now you do what? Well, you do the associated LBM manifolds. L is Lopez de Medrano, V is Verhofsky, M is Messerman, and you do the associated LBM manifolds, and with these explicit things that I could explain a little bit better with an example in a minute, you get this, you get the quantum moment map for the quantum integrable system. And so you get the quantum moment map, and well, everything is very, very, very nice. The Gale transform doesn't affect the associated stack, and then you get the quantum moment map. Let me describe the quantum moment map though with a little picture, because all this was lots of letters, so I'll do a little picture to try to explain the situation. So what is this Gale transform doing? Well, once I have a fan, and I move all these stacks into a stack, then the quantum moment map gives me some sort of polytope dual to this. This was the parameters V, And importantly, the beautiful part here is that the inverse image of a point here is a quantum torus. And the inverse image of a point here is another quantum torus, and the dimension of the quantum torus corresponds to the stratification of the polytope. So out of quantum tori, I'm gluing them up to form a quantum toric variety. And these are, well, these are of course the quantum, the tori of the integrable system, except that now it's a quantum integrable system. And you have all these quantum tori, all of them moving above a polytope. The polytope in the past was forced to be rational. Now it is not. Now it is anything under the world, so it's any polytope. And as you move here, and as you move on the stratification, the dimension of the quantum tori changes, and all these quantum tori unite to form a quantum toric variety. And this is what the Gale transform will do for you.
Do you still have convexes?
Yeah. Yeah, and commuting Hamiltonians. Of course. I'll have to explain what that is. But I can do much better than this. This is just what allowed us to discover the front part. So I can do much better than this. But let me try to explain this. Okay, so now you have this real quantum tori. Above every point, the dimension depends on the stratus, and then you form this quantum toric variety. And this is what the theory of RBM manifolds and the Gale transform will do for you, the quantum geometric invariant theory. And I have been hinting at this all the talk. Because of this miracle that I mentioned, this theorem is true. Of course, you have to pull in the enormous machinery of Laurent to make sense of this statement, but you can do it. And look, there's something fun here. There's a bit of a fun thing here. Look, there's something fun here, unmistakably fun. You remember these letters. And G is a topological thing, let me call it combinatorial. And N is a number. Well, delta is the combinatorics of the fun. And N is a number, the number of B fields, of gerbs, of the arithmetic complexity of the quasi-lattice. The arithmetic complexity of the quasi-lattice. So notice that it's in spirit, it reminds you very much this. There is a topological combinatorial part that sort of fixes the topology, indeed. It fixes the homotopy theory. And then there is a number of marked things, of things that you add to make the modular space not go haywire, not go crazy. And then you get a complex orbifold. What do we know about this orbifold? Nothing, dear topologists. I call to arms. We have to know something about this orbifold. We know nothing about this orbifold. We know the dimension about this orbifold. It would be nice to know things about this orbifold. For example, its topology. And now it's a problem for Fred, really, because a configuration space of points and things and that. It's that kind of thing. It's that kind of mathematics. This modular space you can describe in this way, and then you can study it. As we move H bar. Okay, so, but as I said, this is a theory. It looks like a nice theory, but it has puzzles. In particular, we would like to prove the following statement. We would like to prove that, I wasn't entirely sincere here, there's all these details that I'm omitting in the fine details, but we would like to prove the projectivity theorem that says that the quantum toric variety is projective if and only if it's really a polytope, not something combinatorially so, but not so. These combinatorialists are the devil themselves, and then they can produce these horrible examples, in which there is this thing that should be a polytope, but it quite isn't, and so we would like to prove the classical projectivity theorem. And then you can't. And the reason why you can't, or fortunately you can't, because Laurent with one of his students is about to, but fortunately you can't for a while, and then you have to think, and then Laurent and Ignacio and a group of people, we have been thinking about the thing that this forces you to think in an entirely new field of algebraic geometry that had not been uncovered before. So let me explain this new field of algebraic geometry that had not been uncovered before. And we have decided, by a very serious committee analysis, in which we drank a lot of bottles of coffee, that it should be called chimeric geometry. So, to do this, I have to remind you, though, that the continuum hypothesis is false. So, let me remind you that. So, this is a theorem, physics level of rigor, Freiling. The continuum hypothesis is false. Okay, so let me try to explain that. And by this I mean, you know what I mean. You know what I mean? You know, the first uncountable cardinals, where it is Aleph 1 or not. And the continuum hypothesis would state that it is, and I'm saying that it is not. You see so, let me just say it. Okay? So, what I'm stating is that the continuum hypothesis is false. So, let me prove to you that the continuum hypothesis is false. These are proved by Freiling, and he uses physics, not mathematics. So, you know, of course it's true. So the idea is very beautiful. The continuum, by contradiction, suppose that the continuum hypothesis was true. Then the continuum, you would be able to order the continuum in a well order. So you would have the continuum. For example, you would go to a coffee place where they have these dart games, where you throw darts with your dark big glass of dark coffee. So you try the darts, and how you play the darts? Yeah, the darts. And you would be able to well order the dartboard, the points of the dartboard. But moreover, though, for absolutely any point, the interval SP of previous points of things that are below P would be countable. Would be countable. So, cool. Now we say, well, so we are here, we are in this coffee place with the darts, don't get lost, or location, and now we know that these things are countable, the well ordering, and now we say we get two people, Javier and Santiago, to throw darts to the board. And now we would say, well, the probability that Javier is less than Santiago, now the game changed. Now it matters who is bigger in this ordering. Or Santiago is less than or equal than Javier is 1. Problem is, the probability of x less than s is the probability of a countable set, that is 0. And the probability of s less than x is the probability of a countable set, which is 0. So 0 plus 0 is equal as 0, and so 0 equals 1, so the continuum hypothesis is false. So let's just accept that the continuum hypothesis is false. Well, now I'm going to erase this. So Chimeric geometry. Take the real numbers and take the ring of all functions from there is this Mumford proposal. Mumford says that in mathematics we should not deal with this set, but we should deal with that set. So this is Mumford's proposal. Not Louis, that's another Mumford. The geometry, Mumford's proposal, is that we shouldn't deal with this set, we should deal with this set. So we do that. And we take the ring of all those functions. Take the ring of all those functions. And now we take f, that is those functions whose support is finite, f the finite. Those functions whose support is finite. And this is an ideal. Because if I take two functions whose support is finite, I can add them up, and it's finite, and I can multiply them by anything, and it's finite. So it's definitely an ideal. And, well, then there is a maximal ideal containing f. There's a maximal ideal containing f. And then there is this field of numbers called the hyperreals due to the marvelous Abraham Robinson. And the hyperreals are R mod m. It's a field. It's a maximal ideal. It's a field. So this is the field of the hyperreals. This somehow could not entirely please Robinson, who hated this statement here. He would say, no. Better take, be serious, man, please, and better add a proposition to your universe. And now deal with the consequences. Well, it is, fortunately, we know now that it's equivalent to do this than to do that. Fortunately, we know it is absolutely equivalent to take this maximal ideal than to add this proposition to your universe. But what that implies is that there exists a number that is bigger than 0 in this field. Well, it implies many things. Let me tell you what it implies. This field contains the real numbers as a subfield. But it also contains these numbers that are called infinitesimals. And of course, it also contains, why not, the inverses of the infinitesimals. And you get the idea. In fact, you can, and we will need to iterate this process a little bit, not so much so as to get to the absolute arithmetic continuum, but if you want to think of the absolute arithmetic continuum, think about it. It's not, won't harm the exposition at all. Okay, so I remind you, this is well known, that to have M is the same as to have something called an ultrafilter. It is exactly the same thing to have M as to have a ultrafilter. So it is that thing. People that talk often to Timothy Gendron, and he was a great source of inspiration to all this, will know that the definition of this very well. So you get this maximal ideal, and it is the same as to have a set of sets, so that the natural numbers belong to the set, a set of numbers, so that the natural number belongs to the set, so that two elements in the set, the intersection remains in the set, it's closed on the intersections, and it's closed under this thingy, containing thing, and the empty set is definitely not in S, and cofinite sets are in S. So that thing is so-called ultra filter. Anyway, oh no, I'm lying. There's more properties. Obviously, I know them very well. Either U or U complement, the union one or the other kind of the ideal condition, and very importantly, the way to relate the maximal ideal and the ultra filter is 8. Exactly that condition relates the maximal ideal to the ultra filter. Exactly that condition. So there is this ultra filter thingy, and now there is this thing, amazing. It's linearly ordered fields. Linearly ordered fields, it is a non-Archimedean field, of course, and there exists this thing, and then there is the infinitesimals, and then there is the unlimited numbers, and then there is the limited numbers that contain the numbers and the infinitesimal numbers, and they are not a field, but they are a ring, and they contain a maximal ideal, the real numbers. So the real numbers, the infinitesimal numbers, are a maximal ideal in a limited numbers, and then there is an exact sequence, and this exact sequence I will call the shadow. And some people call it the standardization, but I will call the shadow. I mean, different people call them different things. I think at least it has at least these two names. Shadow is a little bit more poetic than standardization, so we'll use shadow. Anyway, this is standard, and the thing is that the shadow of X plus epsilon is X. That's the whole point of this gadget. So there is a beautiful example, well known. So remember, elements here were sequences of, were functions, so there were sequences of numbers. So, well, equivalent relations under the maximal idea, but anyway, given a function from the reals to the reals, one can Robinson transfer it by just applying it to every component. Not a problem at all. We just apply it to every component, and we get a transfer into the hyperreals. And there is this beautiful theorem that says that if I take f of x plus epsilon minus f of x over epsilon, that's the derivative. No limit involved. It's pure algebra. No analysis required.
But epsilon here is a non-standard number.
It's an infinitesimal.
Which is one of those?
Any of them. You take any epsilon and do this. You just take any and do this. It's in the field though. It's in our star. Epsilon lives here. The star.
Epsilon is now one of the cardinal numbers.
It's an infinitesimal number. It says at the very bottom. It's an infinitesimal number. For every element in the infinitesimals. Anyhow, R star is unique if and only if the false continuum hypothesis. Luckily, the continuum hypothesis is false. So we have a plethora of R stars to work with, and we can also have fun with that. I may say something on that. So R star is unique if and only if the continuum hypothesis, and the field is non-Archimedean, of course. Field is non-Archimedean. But it's not hard at all to see that you could repeat the same for the natural numbers and the integer numbers and the rational numbers and the complex numbers. Nothing stops you from doing that. And then there is this concept, beautiful concept of hyperinteger, that is an infinite integer number so that all the previous natural numbers, or an infinite natural number, so that all the previous natural numbers is an uncountable set. Nevertheless, it makes sense, perfect sense, to ask whether it's even or odd, or whether it is prime or not. This question makes sense. Anyway, Alan Kohn doesn't quite like it. In 1995, he calls the theory inadequate. In 1997, he calls it décevant. In 2000, he calls it very bad. In 2000, he calls it a chimera. I love that. So we decided to call it chimeric geometry. A chimera. In 2001, he calls it, he says that it has an absolutely major flaw. The theory remains virtual. In 2007, he says that it is doomed to failure. And in 2007, he says, this is the end of the road for being explicit. With that caveat, we just press on. Chimeric algebraic geometry. Chach will be called from now on. So, this has been developed by Katsakov, Otero, Merseman, Verkhovsky. So we have Chach. It contains Ach. Over the non-Archimedean field. What I'm saying is that it is not Ach over star C. I could have done this for any field, by the way. I didn't need to do it over Z. I can take any field and do the same. But Chach contains Ach over any field, any chimeric field. Especially because while Ach studies polynomials, Ach studies polynomials. Chach studies hypernomials, where the number of terms in the summation is uncountable. The number of terms in the summation is uncountable. So, Ach is strictly contained in Chach. And, oh no! I don't know how it does that. Arrow. But there is a beautiful theorem by Ignacio Otero here that says the fundamental theorem of algebra, of chimeric algebra. It says that any chimeric nomial has exactly n roots, where n is uncountable. Exactly n though. And it also says, well, it implies chimeric Bezout. Now we have chimeric Null-Stellensatz, don't we? We have the chimeric Hilbert Null-Stellensatz. Notice that you cannot prove this by Robinson transference or by classical algebraic geometry. It won't fly. It's something else. But now we have the Hilbert Null-Stellensatz, the fundamental theorem of chimeric algebra, the chimeric Hilbert Null-Stellensatz, blah, blah, blah. So let me close this talk. By explaining what does this has to do with quantum mechanics. Because my claim is that chimeric geometry is the correct language for quantum mechanics. So let me explain that. Whole point is you can do chimeric toric varieties. You just do star z to the d inside star r to the d. And you do the thing. You do your thing. And now, chimeric v, chimeric Planck, you look into the infinite and hit the first point. So you get chimeric Planck. And now, well, we have the chimeric Gordon lemma. Otero has proved the chimeric Gordon lemma. And we have chimeric Toric varieties. Now, for example, the image of the moment map could be a solid circle. It could perfectly be a solid circle, the image of the moment map. Well, when it is not a solid circle, when it is an irrational polytope, the shadow of a chimeric Toric variety is a quantum Toric variety. So this theory strictly generalizes quantum Toric geometry. So chimeric Toric geometry, here it is what I just said. X chimeric goes to X quantum. Blah, 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 blah. And blah, 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 blah. You also have developed a beautiful theory of chimeric sand piles that has unexpected consequence, especially for our theory of the origin of life, and etc. Well, for now, that's all.
Preguntas. I have one, Ernesto, but once you bring up ultrafilters as concept, you cannot calculate anything, because an ultrafilter is something that exists, but you don't know exactly what it is.
Let me tell you why that it's true and untrue. If you go about life, remembering every day that most numbers between 0 and 1 are uncomputable, you would readily admit that you cannot compute anything. Or let me say it in another way. If you go about life remembering every day that every real number is really a sequence of rational numbers identified in a complicated fashion, you may get a little bit nervous. Nevertheless, when geometry dictates the path, sometimes miraculously you can even compute some things. Sad truth is, there is this beautiful aphorism by Nassim Taleb that says, physicists can compute, but they cannot define. Mathematicians can define, but they cannot compute. So, truth is, we can compute nearly nothing in mathematics. And this is very tragic. Or not. Maybe it's what makes it so much fun. This is not exactly true. Given that we have produced a cohomological theory for a lot of these things, we have actually computed things. Let me tell you what a computation may look like. Oh, here it is, a computation. We computed the exact number of roots of this polynomial. The exact number of roots of this polynomial. Now, your answer depends on your version of the continuum hypothesis. All right. Why not?
But so, second question, if you this depends on the non-continuum hypothesis.
No, it doesn't. You can assume the continuum hypothesis and then you get a unique answer. But it's much less fun.
Let's suppose the size of the reals is the third infinity. First, so what does it say?
I have no idea. I'm not that advanced in this story, you know. We have been developing the classical cohomological and homotopical theory.
But it must rely on which infinity is the...
And that's a good thing. And that's a good thing.
Any other question? Ernesto, muchísimas gracias.
So the next talk is at 3.